Okay, so one final example problem, number 3. This is also a polar coordinate problem. This one's very similar to example problem 2 with one major difference. And what that is, let's read the problem statement. So the slotted arm revolves in the horizontal plane about the fixed vertical axis through O. So this thing is rotating counterclockwise, and O is a vertical axis. So this is rotating parallel to your desktop, parallel to the floor, so it's rotating in a horizontal plane. So the weight of the thing will be acting into the page. That actually won't appear on our free body diagram, you'll see in just a second. So what else is happening here? We have this slider, this 3-pound mass slider is drawn toward O at the constant rate of 2 inches per second by pulling the cord S. So we have this cord here that's attached to this block. It's being pulled at 2 inches per second so that the block moves toward O. Otherwise, the block would move out towards the end of the slotted guide. So the block is being moved, pulled inward at 2 inches per second. At the instant for which r equals 9 inches, so the radial distance is 9 inches, the arm has a counterclockwise angular velocity of 6 radians per second, but is slowing down at 2 radians per second squared. So at this instant, let's find the tension in that cable and the normal force exerted on the slider by the sides of the smooth radial slot. So this block is in there, or this slider, so there's some normal force holding it in the slotted guide, obviously. So free body diagram is very simple. We just have the tension of the cable, T, away from the body, so the tension is pulling the block so that it moves towards O. And then I'll arbitrarily assume this normal force is in that direction. I could assume it to be in the other direction. And regardless of what direction I assume, if I get a positive result, that means my assumption was correct. If I get a negative result, it means I was incorrect. So we'll go with, let me just erase this. So we'll go with this normal force. Coordinate system. So there's the R direction, as always, and the theta direction would be there. Let's make a little table of what we know. So R is 9 inches. Let's go ahead and convert that to feet. That'd be 0.75 feet. And so R is changing over time because the cable's pulling the block in at 2 inches per second, so that's being drawn inward. So that'd be in the negative R direction, so minus 2 inches per second. Let's go ahead and convert that to, that would be 0.1667 feet per second. And that's a constant. That's a constant value, so what does that tell us about R dot? R dot would be 0 if R double dot would be 0 if R dot is constant. So then theta, not really given, but we don't need it since T is in the R direction and N is in the theta direction. But we're told theta dot, so we have some angular velocity of 6 radians per second, but it's slowing down, so what does that tell us about theta double dot? It would be the minus 2 radians per second squared. So just like the previous problem, I'll just sum forces in the two directions. So let's sum forces. I'll start with the R direction this time. So sum forces in the R direction would be equal to M times AR, which is R double dot minus R theta dot squared. So R double dot is 0, so that'll go to 0. We know R and theta dot squared. So well, I'll just sum forces. So what's acting in the R direction? Well, minus T equals what? Minus M R theta dot squared. So there I can solve for the tension in the cable. So T is equal to M. So here, yeah, another important lesson here. I need the mass in slugs. So that'll be 3 pounds mass divided by this G sub C, 32.2 pound mass feet per pound of force second squared. So again, that's just my mass in slugs times R 0.75 feet times theta dot squared, 6 radians per second squared, and we're through with the tension. Let me write the answer over here just so I have a little more room. So 2.52 pounds force would cause that block to move inward at 2 inches per second. So there's T. So now I need to sum forces in the theta direction. So sum forces in the theta direction is equal to mass times acceleration in the theta direction, where that's r theta double dot plus 2r dot theta dot. So what's acting in the theta direction? Just n equals what? Well, what can we cancel out here? Can we cancel anything? So theta dot, theta double dot is negative 2 r dot. So we need to keep all of these terms actually. So n is equal to what? M times r theta double dot plus 2 r dot theta dot. So I will get a positive result. So n equals the mass in slugs there's the mass in slugs times the radius, or r, 0.75 feet, times theta double dot minus 2 radians per second squared, and then plus 2 times r dot negative 0.1667 feet per second times theta dot 6 radians per second. I ran out of room. Yeah, so let's take a look at our units. So pound mass would cancel. And so here I have feet times radians per second squared. That would give me feet per second squared. So I am left with units of pounds force. So just plug and chug. And that would give me 0.326 pounds force. And I got a positive result, so it is in the direction. It is in that direction. So the bottom part of the slider over here is pushing up on the block, on the slider at that instant.